So thanks for the trust you put into me. I would perhaps need some shot of coffee, or rather some real drink to survive this. Dmitry approached me yesterday by phone telling that he couldn't make it to come and that he's sending the slides, and he was sure I could easily just follow his slides because I know all the stuff, which is just not true. And our collaboration with Dmitry goes back many years, but we wrote just one paper together, which was not linked to this at all. And this about 15 years back, when he was in Brno, he was interested in the geometry of vision. And the geometry of vision in those days was concerning rather what's happening in the visual cortexes 1 and 2, which I remember quite well still, but his today's lecture is rather related to how the muscles operate the eyeball in order to allow us to see anything. So let me give it a try, and I will try to convince you that there is a very beautiful mathematics there, and I will try also to indicate that actually the whole thing is much more complicated when we will just put it all together. So how does it work? It doesn't work at all. Now it does. No, it does here. So as usual, Dmitry's lectures are very dense and compact, and he has got a lot of text there, and he reads it very fast. Whereas my lectures usually have only a few slides, and I'm talking a lot and slowly. So let's see how we end up. So as you see, the human visual system is really quite complicated thing, because you have the retina in your eye, which is actually no way working as what we could imagine being something like a TV screen with pixels. So actually there is very complicated structure with many layers, and there was one Nobel Prize for understanding this by Hubel and others something like 50 years back. So from the retina, the signals go through the lateral geniculate nucleus, LGN, which shares somehow the information, perhaps passes it further to the visual cortex in the brain, but also sends the feedback to the muscles around the eye. And then what happens in the visual cortex is much more complicated. I will come back to that a little bit later. So geometrically, the beginning in the eye is the simplest thing. It can be understood as a central projection. You would see it on this, right? So you have the say point you want to see somewhere A, which will be shown at the retina as the underbar A, and it goes through the eye, through the lens. So it's like a central projection. So what we see is you have the retina, which is part of the sphere. So it's about 2/3 of the boundary of the ball, and the input function can be then considered as a intensity function of what you see, and that's the key point of the whole thing, because actually, as I already indicated, it's no way true that the retina would work as some pixels telling here it's the intensity, here is this intensity, and you would just push it forward to the brain, because what the brain can recognize is just only the change of the intensity, not the intensity itself. And moreover, because it's much more useful, the human brain vision, and the same is nearly all the animals having eyes as we do, is that actually that's the internal structure of the retina which allows to distill rather the information about the contours than the intensity at points themselves, and therefore we see so well the changing contours. So for example, if you play, I don't know, tennis, so you might notice that you see the balls and you understand the movement of the balls much faster if you are moving yourself. If you stay and fix your eyes, it's much more difficult to recognize how they are moving. So this is what the retina actually does, and how does it work? So here we can skip the picture. So that's how the bulb looks like. This is what we saw already, and so via the LGN, which is responsible for the feedback to the muscles, I guess, it goes to the visual cortex, and in the visual cortex you have something. In the visual cortex 1 and 2 there is something which is called pinwheels. So actually the visual cortex realizes in a planar way something which is actually a 2D version of a 3D thing, because what the retina does, it's actually actively working as a blow up of the part of the sphere by one-dimensional projective space of all the directions. So at each point of the retina, you rather have the ability to see how the intensity would be changing in all the directions. Of course, it's all discretized, so you have, I don't know how many, 12 or 27 or how many different pins in your wheel, and this is organized in your visual cortex in a plain version, just having one next to the other. And what you get from the retina is the information that the information is changing along this particular direction. But how does this happen? So it happens, that's another complicated picture. So I think we shall not go directly through that, but you see the LGN in the middle somewhere on the way, and you see the bulb and the message going through the visual cortexes. So maybe just to understand how much more complicated it is than we may imagine. So in the visual cortex 1, there are the pinwheels, and the pinwheels simply get some information about the direction in which the intensity changes along a contour, right? And because there will be much more information set there, and there is a lot of feed forward and feedback, so each of the pinwheels is actually having a layer of neurons, which is 6 layers there, and 4 of them are feed forward and 2 of them are feedback, and they go immediately to the neighbors. And so the neighbor pinwheel gets the message that there should be something coming to that in that direction. And if it's not coming, if there is nothing there, then it means that actually we were looking at something which is stable, and it's only the way how the visual system is built which makes changing intensities from stable intensities jumps, right? And this is done, so this is another picture of the visual cortexes. So this is then done in the visual cortex 1, and then the visual cortex 2 gets immediately feed forward information from many of the pinwheels, and what's happening in the brain is that we see simply the individual sort of small pieces of the, very small pieces of the contours, whether there is a change of intensity along them or not. And so something like if you imagine a flock of birds, you would just see one individual bird maybe moving somewhere. In the visual cortex 2, it's already integrated, and you can see the whole flock, and you already have the information about where it goes to. So it just is able to see the derivatives of the things. So what's happening actually is, well, I don't know why Dmitry just is hitting the real content which we are coming to, and there's the saccades, drifts and tremors. So actually what the visual system is taking over and bringing to the brain is something which is created by artificial changing of the contours all the time. And in all that is then actually understood via these more or less random movements of our eyes. Is what we are really perceiving is rather stochastic data than some stable data. And these stochastic data are transferred to the brain, and on the way they are filtered. And one of the interesting filters which are very well known in information science are the so-called Gabor filters. And the Gabor filters work in such a way that they measure actually the second jet data of the contour changes, because it's something you can imagine like the Gaussian curve, but made to wiggle. And so it's something like the derivative of those things. So the purpose of all that is that the input function will not be just a stable thing which we could see from the retina, but it's something which should provide us with invariance, some invariant data which are independent of the changes. And what we are getting there is randomly changed things, so we can imagine that after it gets filtered to the brain, what the brain can work with is just a poor invariance, and that will just, in the end of the day, allow us to perceive both the stable objects and the moving objects. So now, well, yet not the slide. Yeah, that's quite interesting how it's done. Now is the first time mentioned here explicitly that actually our eyes are continually moving. We shall see the three special movements of the eyes very soon. So they are called saccades, tremors, and drifts. And it has been experimented with that very much, and already in '67 someone constructed some mechanical device which would be able just to compensate all the movements of the eyes, and it was seen that the people who would get glasses with that compensation lose their vision completely within a couple of seconds. So without this you can't really see anything. And as Dmitry indicates in this slide, so there is a geometric model of the perception of the local structure if the images are stable, which very much reminds a discrete version of the Cartan moving frame method. So we shall hopefully come to that in a couple of minutes. So here we come finally to the three movements. So there are the microsaccades, which are very fast rotational movements of the eyes, of our bulbs. Then there is a drift. So with the microsaccades you get something like 2 to 3 microsaccades each second. But the movement themselves are very fast. So it's thought to be the fastest movement of our parts of body. The drifts are rather moving from one piece of attention to another quite slowly, and tremor is permanent shattering during all these things. And all this is called FEM, fixational eye movements. So this is how we see the external objects which are fixed, which are stable. So for example, it's known that frogs do not have it, and therefore a frog sees the fly only when the fly starts flying. If the fly is sitting next to the frog, it's not eaten, because the frog doesn't know about it. right? So this is quite fascinating. So the characteristics of the movements is easy for us from the point of view of mathematics, because we imagine that the head is fixed and the eyeballs are moving a little bit, right? And the eyeball itself can be identified with the standard three-dimensional ball, and this can be identified with the imaginary quaternions, right? So it is r times I, r times j, plus r times k. That's straightforward. And the sphere is just what it, the sphere can be defined, so I mean the primary position of the sphere of our eyeball can be identified with just having the three parameters 1, 1, 1 with the I, j, and k, and every other position will be characterized by choosing a rotation, right? So if we simply take a rotation and we choose another orthonormal frame. So there is the so-called Donder's law that the position, each position of the eye is determined by the direction of the gaze. So you simply have, if you remember this picture with the eyeball, like a cut of it as a circle. So if you choose a point on your retina, this identifies your gaze, right? So that's the position of the eye. And we write F equals FA by the choice of the point A from the two-dimensional sphere. And the saccade is then a rapid movement, so just rotational movement, which changes the gaze position. So it changes where we are focusing our gaze. So from A to B, just on the bulb you have the two points. And the saccades come with small amplitudes, and it's just a part of the FEMs. So the drift means it's something which happens between two consecutive microsaccades, and that's a slow random movement of small amplitude. So the drifts are bringing us to the situation of a random walk as we saw it in the last talk. And as I told already, each second you have got a few microsaccades, and during the drift, the retina image of an external point is considered as a trajectory in a Brownian motion. So now there are a few principles of how the perception of stable objects during the FEM happens. So the visual system extracts a stochastic information on the retina image, which is something which I alluded to a minute ago, and this is happening during the drift between two saccades. And so at first we are in the frame f of the point B, and then in the new frame of f of C, and that's called remapping. It's quite interesting about how this works, because with the computer tomography and this kind of MRI machines, the neurologists were able really to measure exactly how these things happen. And so it's known that just shortly before the new gaze is planned, the neurons in the visual vortex shoot already, and then there is some activity, and then it goes to the muscles, and it's all absolutely perfectly coordinated, right? And that's what the oculomotor system does. So it gets the information about the frame in the beginning and in the end of the microsaccade, and it sends the copy of this information to the frontal parts of this visual cortex 1 or 2, and it's all sort of melted together with the stochastic data, and as a result we get something like the perception. So what's nice is how the next visual cortex is then integrated, and there are some special ones which are roughly the same at all the animals. I don't remember whether it was the visual cortex 6 or 7, which was just specialized to, well, I think the fifth one is specialized to categorization of objects. So it does really to categorize objects, not based on experience, but just splitting the visual things into categories, right? And then the next one is specialized to distinguish the faces. And it's always distinguishing the faces of your own kind and the predators. And it's the same with horses, and the same with apes, and the same with rabbits, and the same with humans. So the vision then is the result of the interaction of the whole stochastic information with the information about the positions, and this is sufficient to convert the whole information into the understanding or imagining the real world around us. So now we come to the core of Dimitri's talk, as I read quickly through, so I hope to understand his aims, or at least partly I will hit them, I hope. So he is now focusing on the motor ocular system, which has to decide and run and control the movements in the saccades, right? And that's what we shall be talking about now. So in order to understand the things, and this will be now very simple pure mathematics. So if someone got completely lost and uninterested with what I was talking about so far, we can start from scratch, because now it's more or less high school mathematics which comes into the image. So we simply take the standard R4 as the quaternionic algebra. So we take the imaginary quaternions, the R3, by adding the 1, right, and the span of that. And so you see that the imaginary quaternions are nicely sitting in, and there is the standard metric there, so the Euclidean metric. And you see that if you take the unit quaternion, and they're generally known that the quaternions, and they were introduced because of that, this 150 or how many years back, because they can encode the rotation so nicely. So the unit quaternions via the conjugation define rotation, and it's always two of them defining the same rotation, right? So therefore the unit quaternions are actually the spin group in that dimension. And this gives us the principal bundle, which is the projection height from the S3, so the three-dimensional sphere of all the unit entropy subgroup of I. So I is just the index which I overlooked in the first reading and didn't understand the line, but that's then clear from the end. So you simply take the isotropy subgroup, which is SO2, and what you get is the two-dimensional sphere, right? So that's a version how we can understand what's called the Hopf bundle. And the Hopf bundle is the natural, nice H1 equivariant map, because the projection is H1 equivariant with respect to the actions, and we can denote the S, so the two-dimensional. So the L stays there for the name listing sphere, which is the intersection with the span of, you leave the 1 there, J and K, and there is the equator there. Well, this sphere appears as an equator with respect to the poles plus minus I, right? And there is the positive hemisphere, which is written there, and let's call it the north hemisphere, and that's called the listing hemisphere, and the boundary, which is a circle, is called the listing circle. And there is a proposition saying that the Hopf map, so the projection restricted to the positive hemisphere, is a diffeomorphism of the positive hemisphere onto the punctured sphere, which is just the S2E without the minus I. And the image of the circle is just the plus I. So that's how it is. So, I mean, there will be later on a picture of that is the listing sphere, right? So you can see all the information there. Now, there is a listing section because, I mean, in the previous slide we saw the diffeomorphism. So if we go the diffeomorphism the other way around, it can be considered as a section of the bigger thing, and that's called the listing section. And there is this primary frame, which I alluded already to, which comes from picking up exactly the frame consisting of I, J, and K, and nothing else, right? And any other K frame is obtained by conjugation with a quaternion. So that's the next line, and they are called the admissible frames. And the proposition says that if you pick up two different points in the listing hemisphere, the positive one, the northern hemisphere, then there will be a unique geodesics, which is of course a piece of a circle joining the two things, and there is a straightforward explicit description of this geodesics. Right, and now we have to compare this listing sphere with the real eye sphere, because the eye, well, it's 2/3 of this sphere roughly, right? So but it's there, it's the retina. So there are some beliefs or descriptions, or the physiologists perhaps call them the donders and the listings. So there are quite a few misprints, so it's listings upstairs, right? Listings laws, and the interpretation is as follows. So you take the sphere in the Euclidean space, so that's the eye sphere, right? And its boundary it's considered to be in primary position, so it corresponds to the primary frame. And the Donders law says that if the head is fixed, then the configuration space is two-dimensional, of course, because you already heard that it's given by choice of the point on the sphere, and the sphere is two-dimensional. So what could it be? And the position determines the position of the eye. So it means we don't allow the eye to twist, so it just rotates. And the listing law says that the configuration is actually the listing's hemisphere. And the eye position associated to a gaze is again given by this kind of conjugation, so it's just the adjoint action, right, conjugation, and sigma was the listing section. So it's the identification of the two things. So I mean, when I read through the second time during the lunch, I understood what Dmitry yesterday told me, that it's all very simple. It's just too many letters to see everything the first time. So now we are coming back to the saccades, right? So now if you go from one saccade, which, well, if you are interested in a saccade which starts from the gaze direction A and goes to the gaze direction B, and of course this is given by one of these geodesic segments, right? And we know that it's related, so the one on the, so there are the two spheres, one is the listing one and the other one is the eye one, and in one of them we have got the big capital letters, there's the I, and the other one is just the values in the listing section. So there's the small a and b, and this will be a segment, and whenever we take such two things, either in this version of the sphere or the other, it must just give us a unique saccade from one position to the other position. And now the most important thing perhaps comes, because there are naturally three different descriptions on what the saccades can be understood as, right? So how to see the saccades. So the first one is the natural one, is the evolution of the eye position during the saccade movement, right? So it's a segment of the geodesics in the listing hemisphere. The other one is the, well, actually in the eye sphere it's even more natural than the second one, right? The first one is equivalent, but the most interesting in the third one because we can imagine that it can be understood as a curve in the orthogonal group, and this is a segment of the one parametric group of rotation around the axis. So you simply have one axis of rotation only, because it moves along the geodesics, right? So the axis of the rotation will be all the time the same. So actually what you are supposed to do is to choose the axis of the rotation. And now we can relate these three characterizations, and Dmitry introduces the following definition. So you take a unit vector A from the image of the standard sphere of the eye, and then there is the oriented two-dimensional subspace, which is the unit normal to, and it's called the A-listing plane, which is just given you choose the A, you have the gaze, and there will be a normal to that. So it's just a plane, right? And the axis of the rotation, which comes as defining any saccade with initial gaze direction A, must be orthogonal to the A-listing normal. So it belongs to the A-listing plane. Right? So you have a plane of possible axes to go through, and now there is the law of half angle. So the unique saccade comes from gaze A to gaze B in such a way that it's obtained by the rotation around the axis, which is the intersection of the two listing planes, which is again no miracle, because once we know that all the saccade will have only one axis, and if there are two planes allowing it, so it must be in the intersection. So that's nice, and the angle is half of the angles which are cut by the two normal planes, which is again a well-known geometric message. So if we have two consecutive saccades with two distinct axes of rotation from, well, the first couple of gazes and then the second one, just adding the third, A2, then we see that the A1 listing plane is given by span of the two axes, and we know how the A1 listing normal will look like. And finally we can define a Saccadic end cycle, which will be a geodesic polygon, like going by the saccades in a row, right? Because there are several saccades before the first drift happens, right? So you see that that's how it works. Well, actually yes, A1 is AN plus 1, that's okay. And this is identified with the gaze curve, which simply just moves it from between, again, the two spheres. So pi is just the map which makes it. So finally we arrive at the final, well, nearly final theorem. So how am I with time? I get another 10 minutes, or yes, so I'm surprisingly fast. The theorem says that if I have a system of unit vectors, which are the potential axes we want to use, then there exists a unique Saccadic end cycle which is given by these rotations, by these axes. And now, well, of course it might be, right? Not always. And it does exist, it works well if all the triples, then I take the first unit axis, the second unit axis vector, and I, which is the direction which is excluded, right? That's the one which completes it, should be all linearly independent. So all the triples built this way must be linearly independent. And then also all the triples, when I go with the three consecutive axes, are linearly independent. So the first condition is I always take two consecutive ones, and add the excluded I. And the second one is I take all three independent ones. And that's the if and only if condition, right? So we know that a system of n axes gives us a Saccadic cycle if and only if this independence will be there. And if the span of the first and last is the same as the span of j and k, then it means that the initial gaze positions were exactly the excluded I, right? So it just related to the principal primary frame. And now there is a definition that with each vector, so each unit vector, we associate a map which sends it from the listing sphere to the I sphere, and it's acting by conjugation, and that's called the moving vector. So omega A will be the moving vector. I haven't digested why exactly this definition. Let's see. Now the theorem says that, yeah, well, it's roughly speaking coming back to the theorem 1, right? So if we look at the theorem 1, we define under which conditions we define a Saccadic n cycle by a choice of such unit vectors as their axis for the rotation. And now we come back to the same formulation, saying that if we start with the axis of rotation on the other understanding of the sphere, then we get the same conditions. And the physiological interpretation says that the theorem actually reveals that the planning of the Saccadic cycles consists only in planning what the gazes are. So what are the axes? Right? Because if you know the first gaze and the second gaze, then you know that the axis of the rotation will be the intersection of the two orthonormal planes, and that gives you the right instruction for the motor ocular system, or ocular motor system, or what was the name, and the main information is that the angles are automatically defined by the choices of the consecutive axes. So you simply know the angles, right? And that's it. So here are